All right, we're going to get back to section 2.6 here, and I was going to try to finish that up in this video. We're talking about limits at infinity, and basically that is a limit where you are approaching infinity or negative infinity. Okay, so this example would be an example of a limit at infinity. Okay, and let's begin computing this. Now the strategy for many of these problems is going to be to rewrite all of the terms in the form of 1 over x to the r power and then use your limit laws. Okay, so in this problem, let me begin by multiplying the top and the bottom by 1 over u to the fourth. Okay, and if I distribute that into the terms here in the numerator, 4u cubed over u to the fourth would be 4 over u. I'm adding 5 over u to the fourth. In the denominator, 2u to the fourth over u to the fourth, the u to the fourths would cancel. Minus 5u squared over u to the fourth, that'd be a minus 5 over u squared plus 2 over u to the fourth. Okay, and then I can use my limit laws. I could split this into 5 limits, and I don't have that written, but I could, do that on the next line here, and then compute the each individual limit. So the limit as u approaches negative infinity of 4 over u, that'd be 0. The denominator is growing without a bound in the negative direction as the numerator just sits at 4. So the y values are going to be getting very minuscule. They'll be negative numbers, but they'll be getting closer and closer to 0. Okay, plus the limit as u approaches negative infinity over 5 over u to the fourth, that'd be 0. Again, the denominator is going to be growing without a bound as the numerator just sits at a constant. Okay, here, limit of a constant is always the constant. And limit as u approaches negative infinity of 5 over u squared, that'd be 0. Limit as u approaches negative infinity of 2 over u to the fourth, that'd be 0. The denominators are growing without a bound as the numerator just sits at a constant. So the y values are going to be getting closer and closer to 0. 0 over 2 is 0, so the answer is 0. Okay. Now, in algebra, you learn about asymptotes, and we've already mixed that in a lot with this section. But the connection with a limit at infinity is that you'll know a horizontal asymptote at that value then. Okay, so the fact that this limit ended up being 0 means that y equals 0 is a horizontal asymptote. Now that's something I could have known already, before I did this calculation, because whenever the degree of the top is less than the degree of the bottom, y equals 0 is always going to be a horizontal asymptote. Okay, so this is maybe another problem where you could have already known the answer before you even started type thing. Now, of course, show the work, because that's what I'm grading you on there. Now, sometimes a function is going to have an asymptote, but an algebra student wouldn't be able to know that. You see, algebra students are limited into just looking at something that's a polynomial over polynomial. Okay, let's take a look at another example here. In this next problem, we're going to see a function that has 2 horizontal asymptotes. Okay, I want us to compute the limit as x approaches infinity of 3x minus 2 over the square root of 2x squared plus 1, and the limit as x approaches negative infinity of 3x minus 2 over the square root of 2x plus 1, squared plus 1. Okay, before we do that, the square root of x squared is defined to be the absolute value of x, which is x if x is not a negative, and we want the opposite of x if x is a negative. We know that anything coming out of the square root calculation is never going to be a negative. X could be a negative here. So like if x is negative 3 squared is 9, and the square root of 9 is 3, not negative 3. Right? So piece 2 says that if you select a negative number, take the opposite of that. Okay, I had selected negative 3. Well, negative 3 doesn't come out of the calculation, right? I want the opposite of negative 3. Piece 2 says that in general, do that if x is a negative. Okay, otherwise, if x is a positive, you're going to keep that same positive number. Okay. Now I'm going to use this in the calculation here. Now, one thing that I can't do is I can't just compute this limit right off the bat. Okay. Some students maybe want to try to do that, and you can't do that in almost all the problems. All right. So like if I were to plug in infinity, which by the way infinity is not even a number, okay, but I have something that's growing without a bound in the numerator and something that's growing without a bound in the denominator. Infinity over infinity is not a number. Okay, so I wouldn't just conclude that the answer is a 1. Okay, that would be a wrong answer, by the way. Okay, but so that's not the way that we'd want to do any of these problems. Okay, infinity is not a number. So again, the strategy is to rewrite the terms in the form 1 over x to the r and then use your limit laws. Now in this problem, with this radical that we see in the denominator, we're going to begin by multiplying the top and bottom by 1 over the square root of x squared. Okay, now the square root of x squared would be x if x is a positive. Now in this problem, x is approaching infinity. So the square root of x squared would be x. Okay. In the second calculation, I'm approaching negative infinity, and the fact that x would be a negative, then I'd want to use negative x. All right. So in the denominator, okay, 1 over the square root of x squared, that's the same as 1 over x, but I'm going to keep the radical on both of these and combine those to a single radical. And then the next thing I'm going to do is I'm going to split the fraction into 2 fractions, do the same thing with the fraction in the denominator here, split that into 2 fractions. So now my terms are either a constant or they're in the form 1 over x to the r. And now I can use my limit laws. Right? I can split all this up into 4 individual limits. Limit of a constant is always the constant. Okay, limit as x approaches infinity of 1 over x, that's 0. Limit of constant is the constant. Limit as x approaches infinity of 1 over x squared, that's 0. So we end up getting 3 divided by root 2, which is the answer to this limit. How about the next one here? The limit as x approaches negative infinity of 3x minus 2 over the square root of 2x squared plus 1. Well, I'm going to begin the calculation the same way. I'm going to multiply the top and bottom by 1 over the square root of x squared. Okay. And now x is approaching negative infinity. So with x being a negative, I'd want the square root of x squared to be negative x. Okay, now that's going to be the only change in the work if you were to compare what we have here to what I just did in the line right above it. Okay, I'm going to combine these 2 radicals to a single radical. I'm also going to split this fraction into 2 fractions and do the same thing in the denominator, split this fraction into 2 fractions. Then I can use my limit laws. Limit of a constant is always the constant. Limit as x approaches negative infinity of 2 over x, that'd be 0. Limit of a constant is always the constant. Limit as x approaches negative infinity of 1 over x squared, that'd be 0. So we end up getting negative 3 over root 2. Now, I think obviously in these calculations, we need to know this piecewise definition. That's a key part of the calculation, okay? And it matters if you're approaching infinity or negative infinity, because it matters if we are using x or negative x here in that first step. Now, this is a function that would have 2 horizontal asymptotes because of these 2 different numbers that came out with these 2 limits at infinity. Now, an algebra student would not be able to know that, okay? Because we don't have a function of the form polynomial over polynomial, all right? The only way to know the asymptotes is to know calculus. Y equal 3 over root 2 and y equal negative 3 over root 2 are the equations of the horizontal asymptotes. Okay, here's another example. The limit as x approaches infinity of x minus the square root of x squared plus 2x. Okay, now what you don't want to do, again, is you don't want to just replace x with infinity. Some students would want to do that, and that is right off the bat, you've messed the whole thing up, okay? By the way, if you do that, you've missed the idea of infinity. You've completely missed the concept of what we mean by infinity, because infinity minus infinity, well, that's nothing that we can comprehend, right? Infinity is not a number. So if you were to think of the problem as infinity minus infinity is 0, first of all, that's a wrong answer, okay? And second of all, you've missed the idea of what we mean by infinity. Infinity is not a number. So I wouldn't want to think of that, just plug in infinity or something like that, okay? There is, algebraic manipulation that would have to happen here in this problem. So now I'd want to think of the function inside as an expression over 1, okay? And the fact that this has a radical, why don't we go ahead and begin by rationalizing the numerator? Okay, we've seen some problems where we've been doing that already, so let's do that here. Multiply the top and the bottom by the conjugate of the numerator, and when you FOIL out the numerator then, x times x is x squared, the outer and inner terms go to 0, negative times positive is negative. Okay, the square root of x squared plus 2x times the square root of x squared plus 2x, that would be x squared plus 2x. The denominator I'm just going to keep as is. Okay, and then x squared minus x squared, those are gone. You can also distribute the negative 1 there. And so here's where I'm at next. Now, I still cannot plug in infinity. Okay, infinity over infinity is like, that means nothing. Okay, infinity is not a number. So there is still more work to do here. Now, this problem at this point is going to be kind of like what we saw up here. Okay, we've got a radical, and I'm going to multiply the top and the bottom by 1 over the square root of x squared. Now, x is approaching infinity, so the square root of x squared would be x. So when I say 1 over the square root of x squared, that's the same as 1 over x. Right, that's what I was doing up here. I was multiplying the top by 1 over x. Let me do that here. So, well, I'm going to have negative 2 then in the numerator. In the denominator, x times 1 over x would be 1. Now, 1 over x, that's the same as 1 over the square root of x squared. So let me combine this radical with the other radical here, that would be the square root of x squared, into a single radical. And then let me split that fraction into 2 fractions. And now I can use my limit laws. Okay, limit of a constant is always the constant. Limit as x approaches infinity of 2 over x, that'd be 0. And so I end up getting negative 2 divided by 2 is negative 1 is the answer. Okay. By the way, so there's some creativity going on in this problem. And again, this would be another great example of a function that would have an asymptote, and an algebra student would have no idea how to figure that out. Okay, only a calculus student would be able to get this. Y equal negative 1 would be the equation of that horizontal asymptote. Okay, and and that's the point that I'm making. Some functions have horizontal asymptotes, and the only way to know what those equations are is to know limits. Okay, so you got to know calculus. Let's take a look at another example. Okay, how about the limit as x approaches infinity of sine x over x? Well, the limit as x approaches infinity of sine x does not exist, right? Since we know the sine curve oscillates between 1 and negative 1, you're not approaching any one y value as x is heading out towards infinity, right? If it's just bouncing between 1 and negative 1. So I wouldn't want to just split this into 2 limits. Okay, the limit of a quotient is not the quotient of the limits if the numerator does not exist. Now I do know that the sine curve oscillates between 1 and negative 1. I just said that, right? Sine of x will never be bigger than 1 or less than negative 1. Now, I've created a 3-part inequality, and if I multiply throughout these 3 parts by 1 over x, because I see I've got sine x over x originally, and that'll now be my middle part here. And the fact that x is approaching infinity, okay, this inequality would be true when x is greater than 0. If x is less than 0, then this inequality would not be true, because if you multiply throughout an inequality by a negative, you got to flip the signs. Okay, so it actually is important that we say for x greater than 0. Okay, this is not true for all x. Of course, x can't be 0, right? Now, where am I going with all this? Well, I've created a three-part inequality that is on purpose, because where I'm headed next is the squeeze theorem. Okay, the limit as x approaches infinity of negative 1 over x, that's 0. Limit as x approaches infinity of 1 over x, that's 0. So the limit as x approaches infinity of the guy in the middle, sine x over x, that also is 0 by the squeeze theorem. Okay, by the way, the only way to do this problem is by using the squeeze theorem. That is our only option. And I mentioned that, back when we learned the squeeze theorem. The squeeze theorem will come up here and there, okay? And in some problems, there's other ways to do the calculation, but in others, that's your only option. Okay, here's an example of that. Let's take a look at, so here's a theorem next. Let a be greater than 1, okay, then the limit as x approaches infinity of 1 over a to the x, that's 0. The limit as x approaches negative infinity of a to the x, that is 0. So in this limit, the denominator is going to be growing without a bound, as the numerator just sits at 1, so the y values are going to be getting very minuscule, very close to 0. X is approaching negative infinity. A to a negative power would be the same as 1 over a to the power. 1 over a to a power that is increasing without a bound would give you 0 then, right, if the denominator is increasing without a bound. All right, here's an example. Let's find the limit as x approaches infinity of 2e to the x minus 3 divided by 1 plus 5e to the x. Well, I'd want to begin by multiplying the top and the bottom by 1 over e to the x. You see, the plan is to try to, use this theorem that I mentioned above here. I want to get the terms in the form 1 over e to the x, or a constant, okay? So let me distribute 1 over e to the x. I'm going to have 2 minus 3 over e to the x in the numerator, and then 1 over e to the x plus 5 in the denominator. I want the limit as x approaches infinity of that whole thing. Now I can use my limit laws. I can split this into 4 limits. Limit of a constant is always the constant. Same here with the denominator. Okay, the limit as x approaches infinity of 1 over e to the x, that'd be 0. The denominator is growing without a bound as the numerator just sits at 1. This would also be 0. So 2/5 would be my answer. Okay, and I would also conclude that there'd be a horizontal asymptote at y equal 2/5 on this graph, and that would also be a function that an algebra student would not be able to see where the horizontal asymptotes are located. Okay. Now, we talked about infinite limits in section 2.2, right? An infinite limit is one where you get infinity or negative infinity coming out of the calculation. That's different from a limit at infinity. A limit at infinity is where x is approaching infinity or x is approaching negative infinity, all right? So that kind of, just to wrap this section up here, why don't we look at infinite limits at infinity, okay? So here's an example. What if we want to find the limit as x approaches infinity of x to the 5th? Well, x is growing without a bound. So x to the 5th would be growing without a bound. The answer is infinity. Okay. Now what this means to us is that as we head out on the x-axis, the y values are going to increase without a bound. So in quadrant 1, this curve is going to be heading upward and outward. Okay. How about this next example? What if we had the limit as x approaches infinity of x squared minus x? Well, I would not want to think of this as infinity minus infinity is 0. That's an oops, and then some students will want to do that. Okay, don't do that. You've missed the idea of infinity. Okay, infinity is not a number. I've got that mentioned over here. So infinity minus infinity cannot be defined. Okay. Now, what we would want to do x is in common. I can factor that out of these two terms. X is approaching infinity, right? So x is growing without a bound. X minus 1 would be also growing without a bound. And so their product would be growing without a bound then. Okay, you got something growing without a bound multiplied by something growing without a bound. That's going to be something growing without a bound. Infinity is the answer. All right, so this is an infinite limit at infinity. And again, what we would take away from this is that the graph of y equal x squared minus x would be heading upward and outward into quadrant 1 there. Here's another example. Okay, the limit as x approaches infinity of 2x squared minus 5 over 1 minus 3x. Now, when you come up with the multiplier here and then use your limit laws, one thing that you want to make sure does not happen is you can't divide by 0. Okay, so like in this problem, I wouldn't want to multiply the top and the bottom by 1 over x squared, because the limit as x approaches infinity of 1 over x squared is 0. The limit as x approaches infinity of 3 over x, that's 0. That'd be an oops. You can't divide by 0. Okay, so there is, some strategy in this, in that when we think of the multiplier here, we also can't divide by 0. Right? Now, if I were to use 1 over x as a multiplier and then distribute, I'm looking at the limit as x approaches infinity of 2x plus 5 over x divided by 1 over x minus 3. Okay, now I can use my limit laws. Limit as x approaches infinity of 1 over x, that's 0. Limit as x approaches infinity of 5 over x, that's 0. Limit of a constant is always the constant. And now x is growing without a bound, so 2x would be growing without a bound. So in the numerator, I've got something growing without a bound. In the denominator, I've got negative 3. Well, that's going to give me negative infinity, right? If I've got something growing without a bound divided by a negative, I get negative infinity as the answer. All right, so just some examples of infinite limits at infinity there. All right, that's all I had in this section. So the homework is on page 137. Be sure to look at the odd numbered problems listed there for me.